Swayam Prabha. Digital India. Educated India.
Okay, all right. In the previous slide, we saw how the softmax was computed. So now we see how the difference is computed through the matrix form, and then see how that difference is in the target versus the computed value is taken through the computations of our weights in the embedding as well as the context layers, right. Okay, so let me redraw that one more time. So I am going to be using V love NLP and okay. So we will just first get the target value. The target value we are going to be, this is what we have used as the context. So the target is going to be this, right. So this value should be equal to 1 in the real situation. Okay. So this is our target, and then through softmax we have some values associated with each of these. Okay. So now what we do is we have to find the difference in the we need to find the difference between the target and the predicted value. So this is our error, right. So error is also going to have the same size as the target and the predicted value. So we have 1, 2, 3, 4, 5 and 6 value. Okay. So now having computed the error, we have to update the context weight first, right. So how do you get the difference in the context weight? Just taking the value as we have computed earlier. So we have to do this. So we take let me add some space here. So this is our H, right, and this is of size 10 by 1, correct. So when you compute this, what you are going to have is the error that you want to propagate for context weight, right. So when you do that, you get another matrix of size 6 by 10, right. So and this is what you are going to be using to really update the context weight that you have. So we are starting, remember we have error first, and then from there based on the error we are going to update the context weight, and then again based on the error we are going to compute the embedded weights. Okay. So this keeps going until the error reaches a minimum value, correct. So that is what is our back propagation approach. So we do the back propagation, do the forward pass, and then keep going and going and going, okay, until this becomes small. All right. So in the matrix form, how do you really get this? So this is my I am going to only write for the context matrix. Okay. This is our old one. And now we have the difference. So, to get the new one, so what we do is we have wij new equal to, so we have the wij old, okay, minus you have a learning parameter and then the difference that you have here, right, your E dot h. So, once you do this, now you have updated the context weights, correct, and then taking the error back to the embedding layer, we can update the embedding layer weights in the same fashion. Okay. So, once it is updated, so you keep going back and forth until E becomes small. I keep repeating this so that it gets into the minds clearly. Okay. So, for many people the equations are good enough to understand this. For some folks, matrix operations in this form that I have shown is good enough. For others, the programs are important. If you show them through the typical computer program either in C or Python, they grasp it a lot better. So, I am going to be giving the third flavor as well in this exercise after this. Okay. I hope you understand this, right. So, this is a very simple operation that you perform to identify the embedding layer weight and also finding what exactly is the target that you are looking for. The only problem with this is when the size of the vocabulary increases, the size of these matrices are going to increase and it is only a computational problem. How do we really use multiple words? I am sure you understand based on what we have done. We have been talking about the one word learning, right. There is only a bigram that you are looking at. When you provide V, we want the network to learn love. Okay. So, this is a very simple architecture that we have chosen to make you understand the concept of creating the embedding vectors. So, once this operation is completed, so we can actually throw away the context layer and the hidden layer. The embedding layer will give you actually the index of the word that we want to really find. Okay, supposing if you want to find the word vector for love, it is nothing but the index of that row in the embedding matrix. All right. So, now let us take the same thing and extend it to the multiple context word, right. So, when you have multiple words, how do you really take this forward? So, I am going to be talking about only CBOW model and I am going to be providing an example in the skipgram model as well using Python program. Okay. So, now let us look at this multiple words model. In this case, we are going to be taking more than one word as a context word, right. So, in this case, C is the number of context words and then V is the size of the vocabulary, which can vary from 10 to 1 million depending on the size of your corpus. And then in this case, HI receives the average of the vectors of the input. So, in this case, since there are multiple contexts coming in, the H is a linear combination of all of those. So, we call it as an average of the vectors of the input here. And then the computation of the output layer is very similar to what we have done earlier, there is no change there. And then there is an error that is computed. So, we will now have only one again word that we want to find out, right. Based on the context, we want to find the target, right. So, we know what the target is because it is a learning process, and then find the error, do whatever we have to do to minimize the error. So, this is how it works in the multiple words as well. So, if you use the CBOW model for multiple context word, it is very similar except for the input to the hidden layer computation. Okay. So, as I mentioned earlier, so this is how we compute the vectors. The uj is the context vector that you are talking about, correct. So, it is nothing but the context vector, context matrix that we already have, and the dot product of it with the hidden layer values. Okay. And then the hidden layer value is nothing but the set of input context word. So, the H is calculated using this formula, okay, and then it is given as this. Okay. If you do this dot product, you get the rows of each of the embedding matrix. Again, we can find the error. So, we can borrow the equation, borrow from this equation, we can find the error value using the entropy, right. So, and this is what we want to minimize. This is again same as what we had seen earlier. All right. Again, if you look at the updation of weights based on the error, there is no change, correct. And then eta is our learning parameter, which varies from 0.1 to 0.001, or sometimes it could be, and so on. Okay. So, you have to really choose this value to suit your need. All right. So, what does it learn? So, like in the previous case, it learns the distributed representation of words as a vector. Okay. So, as once this is completed, once you have processed all the input combinations and you have provided the input and trained the network, you will have the distributed representation of every word in the vocabulary, right. The learned vectors explicitly encode many linguistic regularities and patterns. So, this is the very important aspect that we have to understand, right. So, we have been talking about this right from the time of LSI, correct. A word is known by the company it keeps. You remember that, that is from the first. That means when the word is surrounded by the similar word several times, then we can really identify what that word means, what that means, and so on. Okay. In the same fashion, if the context surrounds similar words, we will be able to relate those similar words because of the patterns of the context and the regularity that surround that particular central word that we are talking about. So, the vectors that we are talking about in this model will not just have the details related to it alone, it also has some relationship among the similar words and so on and so forth. Okay. So, it is not a single word representation. So, we will see how it is when we go to the example. So, the learning should produce similar word vectors for those words that appeared in similar contexts. How do we find this out? How do we compare those words to find out whether these words occur in the corpus and they are similar? Can we use cosine similarity? For example, if you created one vector and then we have about 1 million word vectors that are created. So, we can take that word and then try to find out the cosine similarity to the rest of the words in the vocabulary, and then using that cosine similarity you will find out how close other words are with the chosen word. Okay. So, this is another one that we can look at in the example. Does it address stemming like run, running, ran, and so on? This really requires the context to be similar in order for us to really combine these similar words. right. So, we definitely require a large corpus that keep using these words in similar contexts. So, if we have different context for each of these words, I am sure no network will really find them out. So, our assumption is based on the FERT, these words can be known by the company it keeps. That means the context words surrounding these run, running and ran would be very similar. Only if they are similar, we would be able to take these as similar words. Okay. See, for example, some examples of he runs half marathon, he ran half marathon, he is running half marathon. So, something like this, to show how we can really relate these words, when we process the corpus. How about car, cars and automobile? So, same explanation hold true here too. Okay, if these words appeared in similar context, then there is a high probability that these words provide higher similarity values. How about these? Especially in the reviews, if you see again similar context, it is possible that these words could be found could be similar. Okay. So, again the context is the king here. So, if you do not have the right context and these words appeared all the time in different contexts, there is no way that we can relate them. Okay. So, that is where these regularities and patterns come into play. So, our basic assumption is these words appear in similar context, and it is true in most of the cases. Okay. That is why most of the applications that we are going to be developing and that are developed show similarities for these words. All right. This is another I am sorry, this is a skipgram model. Okay. So, you have to look at it from this direction. Okay. The input layer is here, and then we have the hidden layer and the output layer. You know well that for the skipgram, we are going to be providing one input word and the target is going to be our context, correct. So, we have the embedding matrix, we have the context matrix and so on. So, what happens here in the skipgram model, when we provide the input, we assume that the word that is output would be its context words. If not, we go back and keep adjusting the weights and so on, right. So, until the word gets its context right. All right. Okay. So, what I just wanted to mention is, with the last one before the slide on skipgram, we have concluded the word to vector using the CBOW model. Okay. So, CBOW model, we have taken the 1 gram. In the CBOW model, we have taken the bigram to identify the target word, okay, and then we have extended it to multiple context words, and then we also had shown how and what they learn, right, through the examples of the matrices. Okay. All right. So, in the next one, as I mentioned earlier, we are going to be talking about this skipgram, and the skipgram you are going to be providing the central word and the target words are our context words, right. The computations are very similar, there is no change. So, what I am going to do right now is I am going to be taking you right into the coding aspect of this. Okay. Okay. So, this is another simple architecture that shows how you can create a a skipgram based model. Here we have the input vector and we are inputting many as our word as input, and then we have a 300 neuron hidden layer, and then we have 100,000 neurons as our output layer, which is same as the vocabulary size. So, when you input this, we expect this to provide you the context, and these values would be higher than the fastfood that you find at the bottom. Okay. So, this is how we actually capture the context and the input word properly.